Hi, my name is Mehki Polo. Over the past 3 months, I have been researching and learning about distributed databases, more specifically, how they process the data that we query for. By the end of this video, you should understand how cloud database systems pull the data that we ask for and why this is significant. In the words of my professor James Wilcox, a database is just a collection of data. So for example, this is a database, and this is a database, and even this is a database. This is what a cloud system typically looks like. On the left, we see a computer that is essentially just a large disk that holds all the data. It does not have the ability to really compute anything, as its main purpose is to store data. To the right, we see computers, which we'll call compute nodes. These only have CPU and RAM, which we'll call main memory. Since they have limited storage, we can only ever operate on a smaller subset of our data at a time. However, they make up for this in computing power. To understand how the system processes data, we must first break it down to its simplest components. Here we have a single node system. This model may look familiar, as it's essentially the same as the compute nodes from our cloud system, only that now it contains its own disk. Single node systems are the foundation of which all databases are built. Back in the day, we could have modeled their database systems in a similar fashion. Some examples of a single node system could be our phones, our laptops, even our computers. For our example, let's keep our system simple and suppose that we have a disk that holds 100 gigabytes of storage, a CPU with only one core and 1 gigabyte of RAM. Although not the most powerful, it can still process the data we'll be working on, albeit slower than most other systems. Data is typically stored on the disk, and whenever we want to query the data, our selected data is pulled from the disk and processed on main memory. Our systems do this as an optimization because processing on memory is orders of magnitude faster than processing on disk. So here's our example data. We have a sales table with customer ID, stock code, item description, quantity, and price. In some cases, we're operating on data sets that are too large to fully fit into our main memory. This data set is an example of that. This table has millions of rows, and the file is bigger than 1 gigabyte, so we cannot fully load it into main memory. For this example, let's say that I'm a store owner, and I want to find which customers and products are producing the most revenue for the store. So I would write a query like this one. This query outputs a table containing customer ID, the stock code for the item they ordered, and an aggregate function that takes the quantity purchased and multiplies it by the price of the item, which calculates the total revenue for the sales of this item to this customer. Like I mentioned before, this data is too large to be fully read in main memory, so what happens when we execute this query? Beneath the hood, the system parses and rewrites the query, creating a parse tree, which is depicted here. Then the system translates this parsed query into relational algebra, which is essentially just some notation that directly translates to our query. Finally, the system runs an optimizer to select the best physical plan based on metadata, which is information about our database that is readily available. This information can be about the data itself, the size of the relation, frequency of values. It all depends on the management system that we're using. At the end of this, we execute our query and return our output. So what is a physical plan? A physical plan is essentially just a plan for what physical operators we're going to use to execute our query. Physical operators are just algorithms that will run on our relation to produce our desired output in the most efficient way possible, often needing to balance main memory usage, among other things. Sometimes we use them to scan through a table and grab tuples with some relation, typically an operand of another relation. This is called a join. Some common algorithms are nested loop join, hash join, and merge join, to name a few. Here, I have a Java implementation. And we see that we use a map for this. This is typical for aggregation queries, as we want to be able to store the actual aggregated pairs and then their group by clause. In our code, we can see that that's essentially what this first for loop does, is that it calculates the revenue and then groups them by their stock code and customer ID for every item in the list. Then in our second set of for loops, we essentially just grab all the information from the maps and sort of format it into the way that we want, which is customer ID, item ID, and then the revenue for our resulting list. And then once it's gone through all of the items in the map, it'll return this. Each physical plan is optimized for data with certain characteristics, which is to say that in some cases, using a hash join is more efficient and faster than using a merge join. Now that you know what happens when we execute a query, I want to go back and talk about processing data in a database system. So how does our tiny system process data if it can't fit it all into main memory? When processing large data like our example data set, the system relies on physical operators to efficiently organize and retrieve the data. One such method is the two-pass hash algorithm, which divides data into disk blocks, the smallest unit of storage on disk, and processes them using memory buffers that are roughly the same size as these blocks. In the first pass, we have a partitioning phase. We say that we have m memory buffers available. We reserve one buffer for reading input data, and we use the other m-1 buffers for partitions on disk. As we scan over the sales table, we apply a hash function to customer ID and stock code values, which determines the partition each record belongs to. Each partition is then stored in a memory buffer until its buffer is full. Then, we write it to a temporary partition file on disk. At the end of this phase, all records with the same customer ID and stock code values are in the same partition, ensuring that each partition is small enough to fit into memory for the next pass. This second pass is called the aggregation phase. We load data one partition at a time into memory. As the records are read, we store them in an in-memory hash table using customer ID and stock code as the key and maintaining a running sum for calculating our revenue. Once all records in our partition are processed, the results are written to the final output. This process is repeated for all partitions until the entire dataset has been processed. By breaking down data into manageable chunks, the two-pass hash algorithm allows the system to process large datasets efficiently, even when they don't fit entirely into main memory. This same concept can be extended from a single node model to a distributed multi-node model, where data is partitioned across multiple nodes to further improve scalability and performance, which we have here. Conceptually, this algorithm operates in the same way. However, we run into another issue. What do we do when the data that we need to read is stored on another node? Using the same algorithm as before, we perform a local aggregation on each node. Since our group by requires rows to be grouped by customer ID and stock code, we need to repartition the data across our three nodes to ensure that records with the same customer ID and stock code end up in the same node. For this, we can use another hash function that is dependent on customer ID and stock code. This method works since it guarantees that rows with the same ID and stock code end up in the same node. Now that we have partitioned, we can finally compute our aggregate once more locally on each system to get our final result. We can see that when data is distributed across multiple machines, we must often communicate across these machines and send data to compare. This is a very slow operation and one we should try to avoid. This issue has a simple solution. What if we just had them all share one large disk? This is what the database people call the disaggregated model. And notice how it's the same model I showed you at the beginning of this video. That's because it is. We've officially come full circle. This model is the foundation of modern cloud computing. So how does this type of system process the data in our example query? In a disaggregated cloud system, partitioning works a bit differently. Instead of focusing on where the data is stored, we care more about how it's stored and how it's accessed. Since cloud storage is separate from compute, individual nodes don't own specific data permanently. They retrieve what they need, process it, and write it back. For our query, the system follows a rehashing strategy. The first step is to repartition the data. Each node is assigned a range of hash values to process. The data is dynamically rehashed and reassigned based on customer ID and stock code, ensuring that all records belonging to the same group end up on the same node. The second step is to do the local aggregation. Each node computes the aggregation for their hash range. Once this is completed, they write out the output from the temp file to the cloud. This allows the other nodes to access the processed data if further processing is needed. This approach is what makes cloud databases like Snowflake, BigQuery, and AWS Redshift scalable. Compute and storage scale independently, and data processing happens on demand without the bottleneck of a fixed node ownership. Cloud databases are at the core of modern data processing. powering everything from real-time analytics to machine learning. The disaggregated model has revolutionized how we store and process data, allowing us to scale compute and storage independently. This means that whether you're analyzing petabytes of user data, optimizing supply chains, or simply running a query on your favorite cloud platform, you're benefiting from these concepts in action. As databases continue to evolve, understanding these fundamental ideas like partitioning, distributed processing, and cloud-based execution will be increasingly important for anybody working with data. Thank you all for watching. I hope you learned something new today about how databases actually process your queries under the hood. A huge thank you to my professor James Wilcox for his guidance and essentially making this video possible. If you have any questions or thoughts, please feel free to drop them in the comments.